Welcome to the Computational Fabrication Seminar,
a web series showcasing new research, exciting ideas, and exchanging thoughts.
Our weekly 1-hour live sessions rotate through 3 different topics.
Welcome to the Computational Fabrication Seminar
by ISC Austria, University of Washington, and Singapore University of Technology and Design.
Each session starts with a motivational opening talk given by an expert from industry or a field related to computational fabrication, such as robotics, computer graphics, mechanical engineering, material science, HCI, applied math, design, or architecture.
The motivational talk is followed by a technical deep dive. We invite our audience to ask questions during the talks via YouTube comments and join us afterwards on Discord.
Hello everyone. Welcome to the Computational Fabrication Seminar. Today's topic is assembly-based fabrication. So we invited 2 speakers, Ziqi Wang and Ziqi Wang. We will have a short Q&A section at the end of the talks. So if you have any question, you can post it in the YouTube live chat box on the right of the screen. Our motivational talk is given by Professor Ziqi Wang. Ziqi Wang is currently an associate professor in the Chinese University of Hong Kong. He has served as the associate editor of IEEE, Computer Graphics and Computer Graphics Forum, co-chair of CFS Asia Technical Brief and Poster Program, and program committee members in various research conferences. His current research focuses on computational fabrication and assembly, 3D vision, and point cloud processing, and the user interaction methods for AR. Okay, Professor Ziqi Wang, the stage is yours.
Okay, thank you so much for the introduction. Okay, so let's go into the motivational part first. Okay, in my part, basically, I have 3 topics. Okay, first of all, I will give an introduction on what is computational assembly and also why we want to do computational assembly, why computation can help to create assembly. And after that, I will give a running example, okay, to talk about how we use computational, okay, to help with some projects, okay, a project that in my group has just recently done on Lego static assembly. Then after that, I will give an overview of some research topics that are related to computational assembly. Then after that, I will give the stage to Ziqi. Okay, first of all, there are many objects advances in our modern world, okay? And many objects are actually, no matter small and big, lots of them actually are made by, built by assembly, okay? From architectures, mechanical devices, furniture, and small objects like toys and also like watches, okay? They are made by assemblies. So the question is, what is the general procedure to create a design? Basically, if you want to create a design, a 3D models, a design of an object, okay, 3D objects. First of all, you have some ideas, okay? You may need to do some sketching to sketch your idea out on paper or using computer to sketch your idea. Then after that, you may want to create some virtual model for you to preview the idea, how it looks, okay? And you may also use computer to do some simulation. And then after that, we will create a physical prototype or even the final fabrication. So that's the general design pipeline for creating objects, okay? But how computation are helping, or why we want to do computational assembly, or how computation can help to create this kind of assembly in general. So basically, I can summarize how computation can help us in several ways. First of all, when we have computer or computation, okay, we can use computation to help us to reduce the manual workload in the design process as well as the modeling process. Okay, just a simple example with Lego, okay? If you use some Lego design tools or something like a CAD tool, using those tools, actually, we can quickly create some models, okay? With just drag and drop using the interface, okay? And there are also no constraint on what type of brick, whether you physically has those brick or not. You can actually create it, okay? Virtually in the virtual space, okay? For free. And then the other thing is that after we have a model, we can also perform some kind of simulation. For example, we can simulate the motion, we can simulate the stress and also evaluate the stability. And more than that, we can also do assembly planning. Okay, after we have an assembly created virtually, can we use the computer, do some computation to help us to design what is the procedure to assemble the objects, okay, parts by parts. Okay, and also we can use computer, okay, computational algorithm to help us to generate the instruction for the assembly. And more than that, okay, when you have computer, more than just those CAD tool that I have showed you, after you have created objects or you have created some prototype or after you perform some kind of simulation, you can also go back, okay, use the result of this stage, okay, to go back to the design and then use some computational methods, okay, to try to optimize the design, subject to some physical constraint or fabrication constraint. I think Ziqi, in the second part of today's deep dive, he will talk more about this. Okay. And further than that, of course, nowadays we have so many makers machine, okay, from 3D printer, laser cutting, and so on and so forth. Okay, after we have this kind of machine, they allow us to create something we call a personalized part or customized parts. Okay, so the question is that when you have so much flexibility, okay, if you just need to manually create the design, it's actually too tedious. So that's why computation can help us to meet the goals and also try to overcome the challenges that you can see here. Okay, let's look at an example. Okay, particularly my recent project on how to use computer or algorithm, okay, to create a design. The input to our method is just some user sketch, as you can see here. Let me go back a little bit. Okay, given a user sketch, okay, the user just need to do some sketch in a virtual environment, a 3D world. Then our goal is that we want to create, okay, an assembly, okay, as you can see here. And the assembly should be faithful to the input sketches. And also we have to consider the structural integrity, as well as we try to aim for some simplicity in the design, as you can see here. So how this can be done? Okay, before we look at how this is done, let's look at some background information about Lego Technic, okay, which is the goal of this one example project. Okay, in this project, our goal is to create a Lego Technic assembly. As you can see here, Lego Technic assembly actually has quite a long history, more than 40 decades already. Okay, and when you talk about Lego Technic assembly, this kind of assembly is mostly for frame structures, okay, some mechanical structure, as you can see here. Okay, an existing approach to design this kind of assembly structure, basically there are two. One is we can do trial and error. Okay, as you can see in this video, okay, the designer can directly and manually construct the design, but this always involves a tedious trial and error process that you can see in this small video. How about using some Lego tool those two I just mentioned about those CAD tool? Okay, using those CAD tool, usually the people will create a design by means of drag and drop. Okay, you can select a brick that you want to use, and then you can drag and drop the brick into a certain location to create the design step by step. But as you can imagine, if you want to create something large, okay, the problem is that you have to have lots of tedious manual work in order to create the design. Okay, although there are some advantages of using this kind of CAD tool. Okay, for example, you can preview the result, you can do that. You can also copy and paste and drag and drop. But the problem is it's too tedious, okay, and it's too laborious, okay? So that's why the question is that, is it possible that we can create a computer algorithm that can help us to generate a design rather than manually creating every single brick ourselves? Okay, so what is the computational challenge in case we want to meet the goal I just talked about in this project? Okay, so the first goal is, the first problem in computational assembly for Lego Technic assembly is we have to first be able to consider a diverse types of bricks that you can see here. Because in Lego Technics, we have beams, pins, connectors, axle, and so on and so forth. Okay, as well as different way of connecting them together. Okay, as you can see in this joint structure. So that's why one challenge of Lego Technic assembly or computational assembly at large is that we have to consider the parts as well as their connections. Okay, so this is a typical challenge for computational assembly. And the second big challenge is that when you have computational assembly, it means you have many, many small parts. Okay, you have to connect those small parts together to form the target form, the target shape. But the problem is that when you try to connect them together, there are many, many ways to do it. Okay, just like in Lego Technic, if you just want to create a square, a small line by line square, there are over 30 billion ways to construct it. You can look at this supplemental material to the research paper. Then you can find out how the mathematical equation to try how we evaluate this number. Okay, but this number is huge. And this number is not just huge. I want to highlight these words. discrete. Okay, which means that this involves a compilatory problem. Okay, this is very common also, very common for computational assembly. If you want to do computation for generation of assembly, you usually have to meet the goal of some kind of compilatory search problem. And the third issue or the third challenges about computational assembly is that usually you have to face, okay, various kind of constraints. Okay, for example, typically for the project that we were facing, we have to consider faithfulness to the input sketch. Okay, whether the computer algorithm generated result can be faithful to the user input sketch. Also, whether the assembly can be coherently connected. Okay, because you can imagine if we just simply lay out all the bricks or all the parts in the three-dimensional domains, although they appear virtually to be connected, but if you really build them in the physical world, they may not be connected in real world. So that's why when you are trying to create or trying to generate the assembly, you have to consider the connections and whether the whole structure is coherently connected. So this is also an issue. And further than that, there may be certain kind of deformation. Okay, when you try to use the assembly upon usage. Okay, so that's why when you do the computation generating the assembly structure, you will also need to face certain kinds of structure integrity or structure stability issue. You have to evaluate and also modify the design accordingly to try to improve the structure. And finally, in case you do computational assembly, you don't want to use too much material, right? Okay, if you want to build a structure, you want to use a small amount of material, okay, to build the same structure. So that's why when you try to do the computational assembly generation, you may also want to consider how much material, okay, that we want, that we really need to create the final structure. Can we have some kinds of optimization in our model, try to create an object, create an assembly that can be more simple, that can consume less number of bricks or less number of parts? Okay, so the goal in this project is that in case the user given some sketches, optionally with some kinds of motion annotation, okay, our goal is given this input and also given a database of Lego Tech bricks, okay, our goal is to be able to directly generate a structure that is faithful to the input, coherently connected, simple, symmetric, okay, and also motion, okay. So the result has to try to respect this kind of constraint and also objective. So the question is, how can we design the algorithm to do it? Okay, here I try to give a very brief overview of our algorithm rather than going into details, okay? If you want to know the detail, you can look at the research paper which has been published in SIGGRAPH Asia 2020 already, 2019 already. Okay, first of all, we have been successfully modeled the Lego Tech bricks, as you can see here. We modeled the bricks mathematically as well as the Lego Tech construction together with some objective. Okay, this is the brick set that we have considered, and this is a connection mechanism, okay, that we consider between every possible pair of bricks. Okay, basically we use a graph model to try to model it. Okay, some data structure to model it. Okay, that may be too detailed. Okay, and in order to ensure the input sketch can cover the design, we also convert the input sketch into a graph structure. Okay, and after that, you can imagine this is something we call a set cover problem in computer science, which means in case we have some bricks, okay, this is a set cover problem because if we can arrange a set of bricks in this domain to cover every single nodes and every single edges in this graph, then essentially we can cover the original structure. Okay, so that's why you can see we model the assembly problem as a set. We can model an assembly problem as a set cover problem. Okay, but more than that, just cover is not enough. As I said, you have to make sure, okay, we have sufficient connector, okay, which is collision free and also without any self collision, okay, and also they are physically connected in order to connect every single brick into a coherent structure. Okay, eventually we also model some mathematical formula. I will skip the details on try to think about the deviation, try to avoid a deviation from the input sketch, try to make sure the result, the generated result is symmetry and also compact, as well as simple, gap free, and also collision free, and so on and so forth. So these are the equations. I will skip all the details. Okay, and finally, we also design a two-stage algorithm to try to design try to generate the Lego Tech assembly. After we have those preparation work that I just mentioned about, in the first stage, okay, in the first stage, basically we will try to generate, okay, the beam orientation, because beam is basically an essential part when we try to model Lego Technic assembly. Okay, so that's why the first stage is we try to build a simulated and healing framework. Okay, try to find an optimal, at least locally optimal beam orientation over the entire structure. Okay, in such a way that we can place beam in the whole domain, the 3D object domain, in a more coherent way. Okay, and then in the second stage is we try to create another simulated and healing framework. Okay, in which we design the layout modification operator. Actually, in this project, we have tried many different ways to model the operation, to modify the designs. Okay, and also we have tried different kinds of framework to try to solve the problem. Okay, given the objective function I have just showed you. Okay, we also try to do many different kinds of experiment to try to change the objective function. And actually, it's a quite a tedious work. Eventually, we can come up with the equation and also the operation that I'm going to briefly talk about. Okay, after that, we create the design after the simulation and then generate the design. We also support some kinds of stability analysis, assembly instruction, and also physical assembly at the end. Okay, so this is the overall pipeline. So in the first stage, basically, we try to arrange the beam as you can see here. Okay, especially the beam orientation. Okay, in the first stage. And after we arrange the beam orientation, as you can see here in this small video. Okay, this is the first step in our algorithm. Okay, let me show you. Okay, basically, it tries to arrange the orientation in such a way that the labeling beams can be more coherently collected, okay, visibly in the 3D space. Okay, and then in the second stage, what we try to do is we start with a random layout and then gradually modify the random layout, as you can see here in this small video, using the operator we designed in the simulated and healing framework. Okay, eventually it will try to optimize the objective function I have just showed you. Okay, and then create such a result. Okay, this is the operation. I think I will skip it out. Okay, due to time I have in my part. Okay, and here are more results I just want to share with you to create different kinds of assembly. Simple examples. Okay. Okay. Basically, the whole procedure is guided by the objective function I showed you earlier. Okay, I think I have to skip. And at the end, in our system, we also support some balancing evaluation and also stress analysis. Okay, as well as assemblability, to ensure in case we follow a certain step to construct the model, okay, we can ensure the assemblability without self-collision during the assembly process. Okay, and finally, some results. Okay, so this is a generated result. Okay, produced from this sketch. Okay, and this is another result. Okay, produced from the sketch you can see here. There's quite a number of bricks, okay? There's 1,000 brick generated. Okay, and here is some physical results. Okay, due to time I have, I think I will just quickly go through the rest, okay? Okay, so these are the physical assembly designed by the system, okay, that I just showed you. Okay, you can see the time is actually quite fast. Okay, compared to human design, you can see if you want to design those things, okay, just input the sketch and then the system generate the brick arrangement. It only takes a few seconds for simple models or just a few minutes for more complex model, as you can see here. Okay, and we also did lots of experiments, but due to time, I will skip all these. Okay, for details, you can read the research paper. Okay, so after I talk about this one example at the end of my part, I want to introduce to you some topics, okay, some research topics currently in computational assembly. Okay, I think the first topic is something I just talked about to automatically generate or construct an assembly. Okay, for example, Lego Technic, okay, general or regular Lego bricks, some interlocking elements, paper elements, and also some laser cut parts. Okay, so this is one topic. And the other topic, which is also quite popular, is joint construction. and also 3D interlocking, as you can see here. Because when you have assembly, one important problem in assembly is once you have the individual part, how can you connect the part coherently together as well as stably together? Okay, so that's why there are several works try to explore the problem of joint creation as well as the interlocking. Okay, and next is reconfigurability. Okay, when you construct an assembly, is it possible to construct an assembly in such a way that the assembly can be reconfigured, which means that we can disassemble the assembly or modify the assembly to make it into another form, okay, for practical usage. Okay, so there's some works going on in this area. And also there's some works on assembly, computational assembly, try to create and design assembly that can deliver certain target motions that you can see here in this slide. Okay, finally, there's also some methods try to solve the problem of trying to create assembly-based architectural models, okay? Okay, as well as try to use assembly to help 3D printing, okay, or wooden cardboard design, okay, or wood design, okay. As you can see, in case we have a better assembly construction, okay, actually we can save the time and also save the material or save the support material need when you try to create 3D printed models, okay. For detail, you can look at some of these work. Okay, finally, I also want to share a new direction that I'm working currently, which is trying to use machine learning to try to learn to create assembly, which means that the question here in this topic is, can we create computer algorithms, okay, or AI neural network to help us to generate assembly based on some human designs, okay? This is actually a very challenging topic. To start, actually, we create one work last year in Ziqi Wang, okay. Okay, to start not to be so too ambitious, we try to solve a 2D assembly problem in which we try to create a neural network, okay, which is a graph neural network, okay, to try to learn to set in a self-supervised manner to try to tile a domain, as you can see here in this 3 result, okay, in such a way that the result can try to tile the whole domain and then try to retain the shape, okay, so this is a kind of a 2D assembly, okay. So I think I have already finished my part, okay, on introduction, running example, and also overview the research topic, okay, in 20 minutes roughly. Okay, so now I think I will give the time to Ziqi, and we will take the questions at the end of the whole seminars, right? So let me stop sharing, okay.
Thanks, Philip, for the exciting talk. So our deep dive talk will be given by Ziqi Wang. So Ziqi Wang is currently a PhD candidate at the School of Computer and Communication Sciences at EPFL. He received his bachelor degree in mathematics in 2017 from University of Science and Technology of China. His research interests focus on geometry processing, architecture geometry, and digital fabrication. So Ziqi, the stage is yours.
Okay. Thank you for Peng's nice introduction, and also thank you for Philip's excellent overview of the computational assembly for fabrication. So my name is Ziqi Wang from EPFL. Today, I will continue on the topic about assembly design while going more deep into the algorithmic perspective of the computational assembly design. Second, into timer itself. So assemblies are used everywhere in our daily life. However, design a good assembly needs a lot of effort. In classical design framework, users tune some design parameters to generate assembly geometry, which then be evaluated according to some user-defined objectives. The parameter space can be either discrete numbers to create this interlocking cube, or it can be real numbers to create this topological interlocking half sphere. More design iteration are needed if the result does not meet the user's requirements. So what are these objectives? First, let's look at some previous work about assemblability. The upper one is about avoiding part deadlocking for assembly. The lower one is about minimizing the scaffold usage during the assembly process. The right one is about resolving the collision between assembly structure and robotic arms. Fabrication tools also constrain part geometry. The red bunny, fabricated by a laser cutting machine, need all its parts to be in 2D. The CNC molded Max Planck head, though have more flexibility, requires all its parts to be high field as well. Recent work combines two different techniques to fabricate this rod-like structure. The rod is cut by a laser cutting machine and the connectors are 3D printed, which utilize both advantages from the two machines. In this talk, we will mainly focus on measuring structure stability for assemblies with rigid parts. The first and the most classical problem is to check whether a given assembly can stand on the ground under gravity. The second type of stability tells the assembly process the partial assembly at each assembling stage should be in equilibrium. The third stability is about assembly under multiple loading conditions. This igloo does not only can stand under gravity, but also can stand when the ground is tilted. The last one is the interlocking assembly, which can withhold arbitrary force and torques. I will clarify this later in this talk. Just an add, for more details about recent development on computational assembly design, we welcome you to come to our Eurographics session on May 4th to learn more. The forward design is hard for human. Usually the design problem has multi-objectives and some of them are contradicted even, like assemblability and stability. Higher stability means the joint should be tight enough, but a good assemblability means parts should be easy insert into the structure. The joint should not be so tight. Lastly, some evaluation process, like calculating stress by FEM, may take several minutes or even hours, which significantly slow down the design iteration. That is why we would like to have a fully automatic design tool. Once users select some specific design goals, the tool can produce a set of feasible solutions. This process is often called inverse design. In today's presentation, I'm going to talk about a general framework for the inverse design problem. Particularly, I want to focus on how to design structure-stable assemblies. Then I will discuss how to adopt the general framework into two real applications, the topological interlocking and the global interlocking assemblies. In the end, I will discuss some future works. So our goal is to optimize assemblies part geometry to achieve different types of stability. Here is a spectrum of the stability that is commonly used for assembly design. We order them according to how much external forces the assembly can withstand. Only the assembly inside the practical region are usable for real applications. In this section, we focus on the assembly which is in equilibrium under a single force, mostly the gravity. For example, how to make this two-part assembly in equilibrium under gravity. Before introducing our method, we need to make 3 assumptions. First, all parts must be rigid. Second, friction is ignored. Lastly, the bottom blue part is fixed. Commonly, there are 2 approaches to stabilize the assemblies. One way is to change position of the part's center of gravity, such that its projection stays inside the contact region. Another way is to modify the contact shape to restrict the part's movement. For the first approach, we measure the extrusion portion of the green part, call it W. As you can see, when W is larger than 0.8, or when the assembly is left, it's not stable. But any W that is smaller than 0.8, which is the right, is stable. Here, we need to introduce a very important concept, the invisibility energy, which measures how far an unstable assembly is away from being stable. When the energy function E is 0, the assembly is stable. When the E is larger than 0, the assembly is not stable. For this two-part example, its invisibility energy is a piecewise quadratic function with respect to W. The invisibility energy is often used for constructing nonlinear optimization to design stable assemblies. The second approach is to change the contact shape. However, simple measure the height of the joint does not give us a meaningful invisibility measurement, since this assembly is stable for any non-zero edge, if you assume the part is infinite rigid. When the joint changes, an ideal measurement should be like the right figure, where the invisibility energy drops to 0 as the joint becomes tight. So how can we find a good measurement like this? The core is to measure the green part's collision-free movement. The movement we used for stability test is the infinitesimal rigid motion, like the right. So it's composed of rotational part, which is rotate around the point, plus the translational part, which is just a 2D translation. Ideal in 2D assembly. Ideal, the motion should be infinitesimal. Here, the part is moved. The part moves in a short period of time just for visualization purpose. The motion space of the green part is equal to all collision-free infinitesimal motion that can take the green part out from the blue part. In 2D, since the green part has 3 degrees of freedom, 2 rotation, 1 rotation, 2 translation, its motion space is a 3D cone. So how to compute this motion space is what we are going to talk about. The part's motion is restricted. So the part's motion is restricted by the non-collision constraint of each pair of contact point and contact normals. No collision means that the dot product between the VR, which is the instant velocity at the contact point, and the contact normal should be non-negative. The velocity at the contact point, colored in yellow, is computed by sum of the rotational component, which is the omega cross product with the R, plus the translational component, just the V. Substituted into the constraint, we can rearrange the equation by putting N and R at one side and V and omega at another side. We call the left side the N hat, which is the generalized norm. The right side, the V hat, which is generalized velocity. So for each pair of contact point and normals, it corresponding to a linear non-collision constraint. Suppose N is the set of all generalized norms, then the motion space is the dual cone of the generalized normal set. And so from some convexity theorem tell us that V must be a convex cone. Now we can draw the motion space for each contact shape. We can see the volume of the cone decrease from planar joint to tangent joint, tangent mortise joint, and in the end, the joint just become the plus y vector. The motion cone just become the plus y vector. However, the motion in the motion space is not always physically achievable. Like translating the green part along plus y direction is collision-free, but won't happen in gravity field. The reason is that the instant velocity at the green part's center of gravity should decrease its gravity potential. The dot product between VC and G should be non-negative. Substituting the VC with omega cross product with RC, which is the position of the center of gravity, plus V, we have this equation, and we also can do same rewriting, like putting G and RC at one side and V and omega on the other side. Now we can use the similar notation to define the generalized gravity. So assembly is not stable if its motion can satisfy both gravity constraints and non-collision constraint. Geometrically, the gravity constraint is defined by a half space, and the non-collision constraint are defined by a cone. The intersection volume between them actually measure the structure infeasibility. However, so the larger the volume is less stable, or is far away from being stable. However, this measurement is not easy to compute and hard to be extended for general cases. An efficient way is to set up this convex optimization as an equilibrium test, which outputs 0 when the given assembly is stable. Here, the optimization encourages the green part to have a velocity that decreases its gravity potential while avoiding collision. However, this test is unbounded for unstable assembly. Any collision-free velocity v belongs to the motion space is also collision-free if you scale it. So the objective function will explode. Thus, we need to add a regularization term, the negative square root norm of the generalized velocity to the objective function to avoid this infinity problem. This formulation turns out to be a good measurement, which can be used for shape optimization. The measurement can be extended to multi-part assembly easily. The collision constraints now are set for each pair of adjacent parts. It's no longer between P1 and P2, but also P2 and P3. The objective function is almost the same, where we just stack all parts general velocity and general gravity to get the hat V and hat G. This measurement is a quadratic programming with linear inequality constraint A. Here, the matrix A is computed by contact geometry, and hat G is computed by part geometry. Recent papers have provided many ways to compute the first derivative of this diffusibility energy using a sensitive analyze. Specifically, we can use the fact that any optimal solution for a QP problem should satisfy the KKT conditions, which is composed of optimality for Lagrangian function, the slacking condition, the original inequality constraints, and the non-negative constraint for dual variables. Then we can do a classic sensitive analyze for this KKT system to compute the derivatives. Having the derivatives, we can use some off-shelf method to minimize infeasibility energy with respect to parts and context geometry. The method finds a feasible solution when the final infeasible energy becomes 0. This is an example. We modify the contact shape such that the left unstable stacking puzzles become stable. Another fabricated Christmas tree models, which is originally is not stable and stable after optimization. By summing up all infeasibility energy at every step of the assembly process, we can define a new infeasibility energy such that optimized assembly is stable at every step of its assembling process. Here is an example of Leaning Tower, which is stable at every step of its assembly. Okay, the general framework is done. We move to our first application about designing topological interlocking assemblies. In the first application, we are going to investigate how to use convex rigid blocks, which can be simply cut from stone, to assemble a 3D masonry structure that is structurally stable without using any mortar or glue. Using convex blocks to build a structurally stable assembly is a very interesting yet challenging research problem. Let's start with this pavement with hexagonal blocks, since we can easily take each block out. This pavement is not geometrically stable. Thus, we are interested in finding another type of block and properly arrange them such that each block is immobilized by its neighbors. Here is a simple example of this kind of arrangement, which is just composed of cubes. The dark gray blocks are fixed boundary. Let's have a look at the purple block and its neighbor. The zooming view shows that the purple block is immobilized as long as the neighbor are fixed. In fact, this kind of pavement has been studied in many other areas, which is called the topological interlocking assemblies. In mechanical engineering, researchers experimentally test the structural stability of this structure. Surprisingly, these cubes are not only in equilibrium under gravity, but also can withhold other types of external forces, like the center compression force shown in the left image. In architecture, the famous Abe wall shown on the left also use a similar methodology in which the cubes are replaced with truncated tetrahedral. Actually, there is a connection between topological interlocking and the pavement with hexagonal blocks. Starting from this hexagonal block, let's rotate the normals of its 6 lateral faces. Here, I remove the top and bottom faces of the block in order to see the change of the 6 lateral faces. Then the new block is the intersection of the 6 tilted faces. We still have to truncate the block at top and bottom to make it form a closed shape. During the rotation, the red faces are pointing downward while the blue faces are pointing upward. The vector angle on the top left shows how much each face rotated. Here is an animation shows how the pavement transforms to the topological interlocking cubes. The rotation angle of the faces are shown on the top left. So can we extend this process into 3D? To answer this question, we have to ask ourselves, what is the 3D version of the 2D pavement? I would say it is the self-supporting structure with convex blocks, which can stand under gravity without using any motor or glue. Starting from a self-supporting structure, we can rotate the faces of each block by a same rotational angle to generate a series of topological interlocking structures, just like the 2D case. To explore the more design possibilities, the rotational angle of faces are not the same in the later shape optimization. Here is just for visualization. We find that these topological interlocking assemblies have very good performance in multiple loading conditions, like this igloo, which can tilt by around 30 degrees along different directions. Thus, we want to investigate the third types of stability in our spectrum, where the assembly is stable under multiple external forces. Here, the stability in multi-loading cases is defined by the tilting test. We tilt the ground to see how large the tilting angle can be before the structure is collapsed. For different tilt directions, the maximum tilt angle could be different. For example, we rotate this igloo around plus X direction. We got a maximum tilt angle of 23 degrees. If we tilt around plus Y direction, we got 27 degrees, which is bigger than plus X direction. Because tilting the ground is equivalent to tilt the gravity direction. Here, we use a cone to represent the tilt stability. Each vector inside this cone is the gravity direction for which this igloo is in equilibrium. We also know that our equilibrium formulation is a linear system. The cone must be convex. Thus, the structure stability is just the minimum of the maximum tilt angle in all tilt directions. So let's review the forward design pipeline discussed at the beginning of my presentation. Here, the parameters are the vector angle of contact faces. We construct each block's geometry from these vector angles. The assembly geometry allows us to compute the feasible gravity cone in the end. If the evaluation does not meet the user's requirements, iterations are needed to adjust the parameters as well as the part geometries. However, there are hundreds and thousands of variables in this process, making it very hard for humans to find a good solution. For our inverse design algorithm, we would like to first increase the objective and use shape optimization to find corresponding geometry. Let's explain it in details. To enlarge the feasible cone, we need to include the red gravity direction into the cone. We use the structural infeasibility in previous slides. The infeasible energy for the blue direction inside the cone is 0, while the infeasible energy for the red direction outside the cone is bigger than 0. From previous slides, we know we can use sensitive analyze to compute the first derivatives of the infeasible energy. We then use the LBFGS solver to solve the energy minimization problem for the red direction. But this may not increase the cone because the cone could just shift to the left. The stability measurement, which evaluates the worst case, may not be improved. To enlarge the feasible cone, we have to minimize the energy for multiple directions simultaneously. Besides, we set the constraint for contact to make sure that the structure is valid after optimization. Due to the convexity of the feasible cone, once the infeasible energy drops to 0, the new cone will cover the pyramidal shape, which are defined by the 4 directions. Thus, we increase the structure's tilting stability. We increase the structure's tilting stability. This process can be repeated for several times until its stability stops increasing. Here is animation of iterative optimization process. The top right is a cross-section of the feasible cone, and bottom right is the histogram of the vector angles of all edges. Here are some results from different input surfaces. So in some special cases, the assembly can be global interlocking. The 2 assemblies in the rectangle box are global interlocking. Here is another global interlocking example. The global interlocking means the assembly can withstand arbitrary force and torque, like this minimal roofs example. However, designing this assembly needs a little bit of luck. That leads to our second application. Can we intentionally design these global interlocking assemblies? To answer the question, we need to first understand what is interlocking. Here are 2 assemblies. The P5 is the key part, which is the last part to put in. Once we fix the key part, P5, and one of the rest part, P3, the assembly should be deadlocked. No parts or any subset of parts can be taken out from the assembly. Apparently, the assembly at the left does not meet this requirement, so it is not interlocking. However, to examine the interlocking property in a classical way is very time-consuming. We have to check all parts and subset of parts at the right and see whether one of them can be taken out from the assembly. Instead, we can reapply what we learned from computing the invisible energy in equilibrium test. Here, the non-collision constraints tell us that the relative velocity of the adjacent parts should be constrained by its context motion space. So for example, the P2 and P1, the relative motion between P2 and P1 should be constrained by their context. We already know it can be written as a linear system from previous slides. Once P3 and P5 are fixed, assembly is interlocking if this linear inequality system only has 0 vector as its solution. No part can move in this situation. Because the constraints in force had to be 0. The assembly's invisibility energy under arbitrary force and torques should be 0 as well, which proves that any global interlocking assembly can withstand arbitrary external forces and torques in theory. So the force should be within the material limit. That is why we can put a global interlocking at the end of our stability spectrum. To further facilitate the shape optimization for global interlocking, one possibility is to define an interlocking invisibility. Just like what we did for equilibrium under multiple force, we also want an energy for interlocking. We can simply just summing up all invisibility energy for all possible external force and torques. However, this process is very, very expensive to compute. To find a good measurement, we need to some simplification. Since most of our assembly here are composed of voxels, we can ignore the rotational component and assume the contact normals are axis aligned. Then we can get rid of the hat symbol from both velocity, generalized velocity, as well as the generalized norm. So every variable here is only have 2 coordinates instead of 3. Since the normal are axis aligned, we can just replace them with -x and -y. The N3 is deleted because it basically is in the same direction as N1. So for the contact between P1 and P4, we have 2 separate constraints. One is for the x coordinates and one is for the y coordinates between the P4 and P1. So what that means is the P1 must move faster than, for example, in x direction, P1 must move in faster than P4 to avoid collisions. We can add all other constraints and cluster them in x and y sets. The inequality can visualize just by 2 directional blocking graphs. An edge in this graph, colored in red, means P1 is moving faster than P2 in x direction. If a graph has a cycle inside, that means P1 is faster than P2, P2 is faster than P3, P3 is faster than P1 in x direction. Which turns out to be that P1, P2, P3 have the same velocity in x direction. Also, another cycle in x plus x direction means that all part velocities should be same in x direction. That basically means if a voxelized puzzle is globally interlocking, its 2-directional blocking graph should be strongly connected except the key. The key is special because it has to be taken out to avoid deadlocking. The forward design pipeline needs user to guess the numbers for n by n matrix, which determines the part geometry, to make the assembly and to make the assembly directional blocking graph strongly connected. Here, for example, the graphs are not strongly connected, especially in plus y direction. So we need more design iterations. However, for our inverse design, if we find the design is not interlocking, we first modify the directional blocking graph that makes them strongly connected. And then we find the closest part geometry modification to satisfy this graph modification. Due to the limited time for this talk, I suggest you to read our papers for more details. So extending this directional blocking graphs to test interlocking property for general non-voxelized or non-axis aligned assemblies could have some failure case. For example, here is an, just a second. Here is a topological interlocking half sphere. Though its blocking graph are strongly connected, the parts can move up simultaneously along different directions. This will not be considered in the blocking graph because the blocking graph separates the motion into class Y and class Z or some other directions. But here is like simultaneous movement. The strongly connected requirements for interlocking assembly is just a necessary condition, but not a sufficient condition for this particular assemblies. But still, strongly connected requirement is a good way to eliminate non-feasible solutions in the early design stage. So it's still useful for quickly delete unfeasible solutions. Of course, we can set up non-linear programming to check whether a structure is interlocking or not. Though this test is generally not useful for shape amplification, but still, once we design an assembly, we can use it to verify our solutions. Here is a laser example, which parts are 2D plates. Here is a flower example. We use the 3D voxel puzzle to be its joints. And my colleague and I also try to design a real bench by using our algorithm to beat IKEA furniture. Our bench design is elegant and environmentally friendly without using any glue and nails. Okay, so that's most done for the technical part. I will conclude my talk by say several future works. So in conclusion, we propose the stability spectrum in this talk and explain how to formulate the test for each type of stabilities. Then, based on the user's defined objectives, either we do a graph search to solve this combinatorial problem to create interlocking cube with discrete parameters, or we do nonlinear continuous optimization to find the topological interlocking assemblies with good tilting stability. In the future, I would like to drop. So I assume all parts are rigid, but in the future, I would like to drop the rigid body assumption and consider elastic bodies that are in contact. The contact FEM actually has been widely used in mechanical engineering, also in civil engineering. However, the inverse design, due to its difficulty, is still an open problem. The inverse design here is about how to reduce the stress concentration by changing the contact shape of an assembly. The challenge is that simulating part deformation with contacts is already very time consuming. So if it's a small deformation, you usually solve a larger QP problem. Here, for our infeasibility test, each element is a block, and each block only have one node. But for the FEM simulation, the block have to have multiple tetrahedrons to do the simulation. So it's very slow QP problem. And for a large deformation, you have to solve a series of time-dependent QP problem that's even time inefficient. So doing an inverse design, you need to do a sensitive analysis that will be even more inefficient. Another potential topic is about using contact as a way to increase structure stiffness or increase the structure stiffness non-continuously. So here is a project done by my colleague, which is published in Nature, where they design a unit cell that can be pre-programming to have different stiffness. The main difference between the same uniform cell in different stiffness states is that the upper one has self-collision earlier than the lower one. So they intentionally move some of its parts to intentionally create this self-collision to increase the structure stability. So could we design some kind of microstructure with self-collisions that have more diversity, stiffness, behavior would also be a very interesting topic. And we can combine these microstructures or building blocks to have more interesting assembly in the end, also will be very interesting. So the third potential project is to consider using robotic arms to assemble structures, like this timber assembly. Assembly project, which is done by our colleague at ETH. So the challenging for this project is to avoid collisions between robotic arms and the structure itself. Often designers design the structure first, and then they find a feasible robotic assembly sequence, also the robotic assembly motions to assemble the structure. So it's like a linear pipeline because there are so many constraints. However, consider assembly process in the design could somehow resolve some very hard path planning problem. Sometimes you cannot just find a solution for robot to assemble. It's not because your algorithm is not smart, it's because your design just don't have solutions. So if you can consider this in early stage, or we call it assembly well design, will be very interesting topic to try in the future. Another thing I want to explain here is like why they assemble these beams using this heavy machine to push the joint in. It is because of tolerance. So you have so many tolerance in the real applications, or so many inaccuracies in the real applications that if you not align them carefully, the beam just cannot go in. So the tolerance or inaccuracy can come in from the fabrication techniques, the melting machine, or the material itself. The wood is a live material, so it will expand and shrink if the humidity change. Also, the material is elastic, so it will bend in the gravity, especially in these large scales. And also, you have some alignment problem, and all combined this problem will make the tolerance issue very, very important in the assembly design. So how to deal with these tolerance issues, or how to intentionally design to reduce the tolerance issues will be also a very interesting project. So the last one is about scaffolding. So usually for architectural assemblies, you need tons of scaffolding, which is waste in the end. So for example, here, if you want to assemble this self-supporting masonry structure, you need this massive scaffolding bridge shell to support it, which is almost the second main cost for making these architectures. So can we minimize the total amount of scaffold by adding temporary joints between parts to make the intermediate stage stable, or we use frictions or intentionally use frictions to make them stable in the immediate stage. But in the end, you don't need them because in the end, the structure is stable. Just use them in the intermediate stage will be very interesting topics. Also, can we find a good assembly sequence that don't need so many scaffolding? Well, be also a very interesting project to try in the future. So that's it. Thanks.
Okay, thank you, Ziqi, for the nice presentation. So, okay, so now we have a short Q&A section. So, okay, the first question is for Philip. So you mentioned about using machine learning to solve this computational assembly problem. So we know the one challenge for this computational assembly is the combinatorial complexity. So can you discuss how machine learning can help to address this combinatorial complexity?
Actually, one way that we have tried in our previous attempt is that we try to use a graph neural network. Okay, we try to model the assembly problem. Okay, as a selection problem. Okay, in which our idea is that we can try to create one graph node for each possible candidate location or each possible placement park location, okay, and also the corresponding park type, okay. And after we have this node, we try to connect the nodes together based on whether they have collision or whether they coherently connect to each other. So after we construct such a graph, okay, we try to train a neural network to try to learn, basically using a graph learning approach, okay, to try to learn to select which node has a higher probability, try to avoid collision in the future. Because you can imagine when human looking at a certain domain and then try to fill the domain, human will have the intuition, okay, to try to find out which location are likely to be a better location to put some initial break, right? So that's why we try to, based on this idea, try to create a new network like this, try to predict which location are good location. Okay, so basically this is a self-supervised graph learning approach. But I agree with the audience to say that this is a problem in terms of scalability, because currently in terms of the number of looks in our current design, I think we can only scale up to about a few thousands only. Okay, because in case the number of looks are too large, then the graph neural network, the number of parameters, okay, and also the training time is going to be a problem. So that's why I think in the future, it's possible to try to localize the problem. This is one way. The other way is, as we talk about in the research paper, we may try to integrate some other methods together. Okay, because you think about when we try to do learning-based assembly, this is similar to playing chess. When you play chess, you also have a very huge domain. Okay, when you select a certain move in the chess game, it will also affect future moves. Okay. So in case you look at some recent work in that succeeds AlphaGo. Okay, AlphaGo is a bit old now. Okay, there's some recent work try to solve the problem. Okay, so I think this is a certain potential of using neural network like that to try to solve the problem.
Yeah, I think that will be a very interesting research direction. Okay, so the second question is for Ziqi. So in your presentation, the front part, you mentioned there are two ways to optimize an assembly to make it stable. So one is to optimize the layout. I mean, you're moving just the position of the blocks. The other one is to optimize the geometry, which is the contact. So can you briefly compare these two methods, both theoretically and practically?
So it really depends on what user want. If, for example, if in my topological interlocking assemblies, you cannot just move parts because you have a very specific modeling scheme. So you cannot just simply move them because they are controlled by this kind of phase angles. But for some other type of assemblies, for example, you may encounter with the timber assembly with some spatial structures. That in that sense, you can move the beams because you just need to approximate the surface or probably some volumes. You don't need to care which beams is there or there because as long as the beams can approximate the surface, it's fine. So it depends on so for that part, it really depends on how users think what they're going to do. But for if you want to consider how effective they are, I suggest the layout is more important than the contact geometries. Because if you're already very unstable, creating a joint only will just increase a high stress concentration on the joint, right? So at least the layout should be close to be stable. Or you can use some fasteners like nails or connectors to compensate this. But if you don't have that, I suggest you to first have a reasonable or very close structure, or you do some layout optimization first to make sure they are close to be stable. Then you just add a joint to even emphasize the stability. Otherwise, even though the structure, or you can say in small scale is fine, but if you want to do the large scales, even though the structure is stable, but in the end it's just break because the stress is too high.
Okay. Yeah. Okay. That's reasonable. Okay. So here is one more question for both of you. Okay. So we know from your talks, we know that so currently there are lots of works to optimize assembly for different purposes. For example, structure stability, assemblability, construction, packing, or fabricability, all these kind of things. So, but when people design some assemblies as products, they don't just care about these aspects. They also care about the functionality. For example, when people design a chair or any furniture, I mean, stability is just one necessary condition. So can you discuss how to take this functionality into consideration in the computational design process?
Yeah, I think one way is try to do it in a case-by-case manner. Okay, rather than trying to be general, okay, I think it's a very tough problem. If you want to have a general framework that can solve functionality, it's too tough. So I think one way is to be case by case. For example, you just want to create chair. Okay, you may try to create a framework tailored for chair, for example. Then you can because for certain objects, it is possible that you can have certain kinds of specific requirement in terms of functionality.
Okay.
Then that will make the problem more easy to solve in terms of optimization.
Yeah, that's true. That's true.
So how about Ziqi? You have other opinions?
So my opinion is like, you have to see what exactly the functionality is. It's like, it's easy to do or not easy to do. Sometimes you just want the appearance to appealing the users, or you want them to look nice, or you want to sit. That's some kind of functionality, maybe easy to handle. But for some global problem like stability or structure concentration, which is very hard for users, then they need some kind of our tools. But our tools is not like dominate this design process. We will use them to find more possibilities, and they select something they like. So it's not like one iteration is done. You have to do multi iterations, but we need to identify which problem can be solved by computers and which problem should be done by the designers.
Yeah, that's true. So it's like the combined interactive and the computational design.
Yeah, that's what I feel for real applications.
Yeah, that's true. Okay, so due to the limited time, so we will move to Discord, and so thank you for speakers. So this is the end of this seminar.
Yeah.
Okay. Bye.
For the host. Okay. Bye.
Thanks.
Bye. Yeah. So see you in the Discord.